guess, instrumental record of temperature change across kind of global average across the last 150 years or so. And we kind of ruled out that the power of the sun changing was a primary cause of that. So the power of the sun has changed, but not by enough to see the temperature changes that we are seeing. We looked at the effect of volcanoes. So these do give off CO2, which will affect the emissivity term, but that amount that they give off is really small compared to how much is in the atmosphere. And the important thing is that on really short timescales of a few years, after a volcano goes off, this sulfur dioxide gets up into the atmosphere and causes these cloud condensation nuclei to form from sulfuric acid. Now, someone emailed me last night to say that I got it wrong, and I did get it wrong. So I said that sulfuric acid has a very low boiling point, and that means that it condenses out. That is incorrect. It actually has a very high boiling point. I just got that the wrong way around. So basically, sulfuric acid likes to be a liquid because it has a high boiling point. It actually has a low melting point, but anyway, that's, you know, by the by. The point is that it has a very high boiling point, so it basically condenses into a liquid very readily in the atmosphere. Okay, and that causes the clouds to be whiter, to last longer. That primarily affects the albedo term. Okay, it has a small effect on the emissivity, but it's primarily an albedo forcing. And then the next thing we looked at was this internal climate variability. So we're not looking at fluxes of energy into or out of the planet, just redistributing heat around different reservoirs in the Earth system, so between the atmosphere and the ocean. And that was what we were looking at here with the, so matching out the state of the ENSO system, so the El Niño Southern Oscillation, and comparing that with changes in kind of little wiggles up and down on a kind of like a 2 to 5 year kind of time scale in the temperature record. So we're going to be moving on to maybe looking a little bit forwards into the future and how we know that what we've got now is our fault. Just to go back a little bit and look into where we are getting this information from. So if you want to look at the modern climate and identify that that's different, we've changed something, we need to have some baseline of which we're comparing kind of the 20th century to. So we need to know what's been going on over basically the previous 1,000 years. So we've got a bunch of data that we can use for that. So things like satellite, this laser is about as much use as a chocolate teapot. We've got, let's do it with the mouse. We've got satellite information, okay, and instrumental, so that's basically going out and reading thermometers. That's really good because that gives us actual measurements of the state of the climate, but those don't go very far back in time and they're quite spatially limited. Particularly, well, the satellite data is not spatially limited. Well, it's limited in that some data doesn't, for instance, go over the North Pole, but you know, you take those weaknesses with the enormous coverage that we do get. Okay. But once we've basically run out, going back in time of kind of actual observations, we need to rely on these climate proxies. So things like the tree rings, coral reefs, looking at the chemistry of the skeletons of corals, things like that. We could look at ice core records. That tells us quite a lot about the conditions in the polar regions. There's a whole range of things we can get from effectively the geological record. And that's what we've got here. So I have shown this plot before, but in a slightly different form. It was the one that had that grey background, which kind of showed the climate over the last 1,000 years. And that's what's shown in the top figure, except instead of showing that grey envelope, it's the individual proxy records. Okay, so some of these are based on combinations of tree rings or ice cores, or so I think some of them are lake-varved sediments with estimates of paleotemperature from measurements of isotopes in leaves, all kinds of data. But you can see that there's this general kind of climate's been kind of trundling along, maybe some ups and downs, but we're not really not very able to constrain these ups and downs very well at all, okay? Because the proxy records don't exactly agree with each other. So there's a large uncertainty about kind of the little wiggles up and down in climate over the last, I guess this is 2,000 years. But it was maybe a little bit warmer here, then it cools down to here. So this is a period that's sometimes referred to as the Little Ice Age. And then we've got this warming until now. So the black curve here is the actual instrumental data, where we have measurements of the climate directly. So we can do that quite well for the northern hemisphere, and that's largely because scientists who look into past climate and go out and collect all of these tree ring records, they generally live in the northern hemisphere. Okay, so all of the proxy records tend to be near where the scientists live, which means that we have less information about the southern hemisphere and therefore less information about the whole globe. So we might want to just consider just looking at the northern hemisphere because that's where we have the most information, or just look at if we look at the whole globe, we might just think, well, there might be a little bit more uncertainty with our reconstructions going back in time. So it's not just proxy records. We can also look at the modern kind of instrumental records. So what we've got here is I guess the big figure. That's a map showing what the temperature change has been since 1900 to 2012. Okay, so you can see that the position on that plot of where there are dots, where there are data on that. That's got nothing to do with how much data we've got now, because we basically know what the temperature is over the whole planet, kind of everywhere, because we've got satellites and all kinds of fancy stuff. But that plot relies on how many places were measuring temperature in 1901. Okay, so you can see that if we're looking at temperature changes over the last 100 years, that really depends on how good we were at measuring temperature 100 years ago. And you can see large parts of Africa, South America, kind of China, the remote parts of Russia, not a lot of information was being collected. Okay? Certainly over the ocean, there are huge parts of the Southern Ocean, the Pacific, which are almost completely not sampled. Similarly, the polar regions, there are no measurements in Antarctica. There are very few measurements around the North Pole. So there are a number of ways around this, and basically these two plots at the bottom, they're just taking those data and doing some, using a statistical approach where they try and basically extrapolate into these unknown regions, okay, using kind of like regional averages for the 1901 case and then using the modern data to compare. So although we don't really know what's going on in the middle of Africa 100 years ago or in the Pacific, we can kind of extrapolate from the data that we do have. Okay, so you can see this one purple point here, that's largely responsible for this enormous patch of kind of things that we think we know here. So there's some extrapolation going on. But it looks like it doesn't matter. So these are basically those maps, but now looking through time and using the different kind of spatially averaging techniques, and they seem to broadly agree. So even though we don't have a good picture 100 years ago, we're pretty confident that we can kind of work out the relative change since then across the last 150 years. And this is that proxy data again, and I kind of mentioned this before. This is how we test whether greenhouse gases are, the important thing. We try and basically run a bunch of models and compare that to the real data. So this grey kind of shaded kind of thing on the background of the bottom plot, that is that data. Okay, it's just presented in a kind of a combined way to give some estimate of the mean and the uncertainty of climate through time. And the point we were making here was that you can't model this modern change, this modern change here, so this increase in temperature, you can't model that if you just have these models with the thin lines, which are the ones that exclude the greenhouse gas forcing. So this shows that greenhouse gas forcing is important. And these are those forcings that are going into those climate models. Okay, so this is, we think, how the radiative forcing has changed through time. So we have a fairly good idea of how much CO2 has changed. Okay, so we know how much that's changed, and we know the effect of that in terms of how many watts per square meter that has kind of caused the climate system to be in balance. There are also, though, other important gases. So methane is probably one of the other most important ones, but also other things like nitrous oxide, fluorocarbons. So you might have I guess, had the example in geography at school of CFCs being not a greenhouse gas, but they are in fact just destroying the ozone layer, or did destroy the ozone layer, and they did destroy it, but they are also extremely powerful greenhouse gases. You can also see on this plot some of the other effects that go into the models in terms of the effect of changing clouds and putting these aerosols. So these are effectively like anthropogenic volcanoes. So when we burn fossil fuels, it's not just CO2 that goes off into the atmosphere. We will also, I mean, we burn lots of coal. That's got lots of sulfur in it. So that sulfur will go into the atmosphere and act as a cloud condensation nucleus. So that has an effect that's actually reducing the temperature of the planet. Okay. So this is basically just another example of that modeling experiment. So just looking now over the last 150 years, if we just run climate models with natural forcing, so these are changes in the solar flux, the sunspot cycle thing, and volcanoes, things like that, then the grey band is what we model, and you can see that that kind of starts to diverge quite markedly up here from the observations in red. Okay? If we just use the anthropogenic forcing, so if we just said, hey, it's just CO2, we don't match so well in this period, but we match up here. So if we do need to consider all of the forcings. So these natural kind of changes in aerosols and in the solar flux, they are important to explain all of the data, but the thing is to explain the long-term increase, you must have CO2 in your model. Now, it's not just the global average. You can do this experiment, and you can start to model down at a regional scale. Okay, and the uncertainties here are a little bit larger because the finer detail you look, the more variability there is when you do modeling. But you can see here that in I guess the oceans and over land, you need to have the models that include greenhouse gas forcing, so CO2 mostly. Those are the red ones. The ones that don't are the blue lines, and the observations here are the black lines. So to match observations at a regional scale, you have to put in some CO2. So that gives us more confidence that our models are correctly basically attributing the warming that we've seen over the second half of the 20th century to CO2 and greenhouse gas forcings. Now, I'm going to take a little bit of a step aside now from kind of, I guess, the physical climate kind of science and think about how we actually come up with these different scenarios that we might want to model into the future. Okay, so if we want to model into the future, how much climate change, we need to know, things like how much CO2 will there be in the atmosphere? What are we actually going to burn? Okay, what kind of gases are we going to produce? So there are basically, what we've got here is just some schematics of two methods which we could go about this problem. Okay? So there's the sequential approach and the parallel approach. The sequential approach is what climate scientists used to do. So what we used to do is we used to think about, hey, what's our economy and population going to look like? Okay? And how much kind of industrial activity we're going to do, and what kind of things might we consider doing in the future in terms of, switching to renewables or not. And then we say, if we do that, what radiative forcing will we get? How much of each kind of the important gases will be in the atmosphere? Okay? And that's basically an accounting exercise. Okay? Saying how much economy we're going to have, how much oil we're going to burn, that kind of stuff. And then we do some climate modeling and say, well, if we know the atmospheric concentrations of stuff, we can run a climate model, and then we can see how much the climate will change, and then make some assessment about how much that will cost in terms of lives, homes lost, and kind of insurable kind of risk, that kind of stuff. So that's fine. That allows us to work out, if we do a certain kind of make a series of choices, we can then go, oh, well, it's going to have this outcome. So that's no longer what climate scientists do when trying to forecast into the future. And the reason for this is because that first approach it basically doesn't allow our economy or kind of how we run the planet to change and adapt to changes in the climate. So there's this alternative approach, which is basically, because we from the first approach, we kind of roughly know the range of possible, say, CO2 concentrations in the atmosphere across a range of future kind of economic scenarios. We just start with that. We just start with, we're going to start out with a different amount of radiative forcing in the atmosphere. Okay, we're going to say, we're not even going to say which gases they're going to be. We're just going to say it's going to be kind of, there's going to be something that goes on that changes the radiative forcing by a small amount, a large amount, a medium amount. Okay, and we prescribe how that will change through time. And then we say, okay, we run a climate model with those things. We say, well, actually now what kind of gases do we need to do that? Okay, and then that links in and tells us what kind of economy that will then kind of correspond to. And that can then feed back into what then causes those different representative radiative forcings in terms of amounts of greenhouse gases. And then from doing those climate models and then allowing us to modify our economy, we can then actually have a more, I guess, a more accurate impact on I guess us, our human existence, because that then allows the basically how our economy behaves to be reflected in the impacts before the impacts kind of happen. So this is a horrible table. I don't expect you to learn anything in terms of the number. Hopefully you'll learn something, but don't pay too much attention to the numbers. But this is just basically the kind of things that go into these kind of models. So if you look at along the top row, there are basically lots of codes for different emissions scenarios. This is using the old methodology. But basically the things that go into those is we basically have some prediction of, how big the population of the planet will be. Okay, and you maybe start out at 7, and then some scenarios say we're going to grow the population of the planet, and then the population will reduce as people presumably die from climate-related disasters. Or some scenarios just have us going nuts for babies, basically. Okay, and then the next thing that's considered is, how productive is that economy of all these people? How much money do they make? Okay, it really comes just down to money. And then once you've got how many people there are and how much money they make, you then have these kind of things that then allow you to work out some kind of climate parameters. So how much energy is required in that economy to produce $1? Okay, and that's in that second row. So some of these have, us being, this is us now, basically saying this is how efficient our economy is, and then through time we become more efficient as technology improves, as we maybe shift away from making big steel things to making little electric widgets that do things, I don't know. Right? So we might become more efficient in our economies. Okay? All of these scenarios assume that we're going to get better at making money. And then that tells us how much energy we're going to need, and then the last bit is basically the choices about where we get that energy from. Do we get it mostly from coal? Do we get it mostly from non-coal fossil fuels, like gas, oil? Or do we get it from renewable energy? Okay? And they all have different choices. They all have different ultimate climate forcings. And then we end up with these kind of things. So different emission scenarios going forwards will have different CO2 concentrations, different methane concentrations, depending on the economic models used. Other greenhouse gases like nitrous oxide, and that allows us to produce a range of climate forcings from those combinations of greenhouse gases. And the thing to notice here is that there's the uncertainty, the spread that we're seeing here, okay, is not all of that spread is down to uncertainty in how we will behave as a population. Okay, so this is not a kind of a climate science uncertainty. This is not like our models are terribly bad and they don't give us very accurate forecasts. This is just we don't really know what decisions politicians will make in the future. I should have deleted that. And these are the representative concentration pathways that are used in the newer sets of climate models for the most recent assessment of the international intergovernmental panel on climate change. So you can see that there's one that's called RCP 8.5. That just means that we're going to have 8.5 watts per square metre higher at the end of the century emissions. And then that corresponds to this much CO2. And that's that one. This one would be bad. I guess the new thing for the most recent set of assessments is they have included a pathway down here which has got a negative slope. So that involves actively removing carbon dioxide out of the atmosphere, or removing some other radiative gas that's just as important as carbon dioxide, which there isn't. So that one uses that geoengineering kind of mechanism, which is effectively magic because it currently doesn't work. And once we've got those radiative forcings, we can project what the climate will do. So this projects actually forward 300 years into the future. So you can see if we follow the RCP 8.5, that will result by the end of the century, which is about here, that will be about a 4 degrees Celsius warming overall. Whereas if we follow let's do some geoengineering one, which is the 2.6, that gets us down to maybe just over 1.5 degrees. So that's the one we want. Not going to happen, but hey-ho. But it's not just about the average temperature. It's not about the average temperature. I mentioned this earlier on in the course. There are also regional patterns. So what we've got here is a set of little things, maps of how the temperature will change regionally. So this is, on the left, we have the average, temperature, the average annual temperature for the period 2016 to 2035. So that's basically now. Okay, so it's the average temperature from now into the next kind of 15 years or so. And you can see that it's going to be warmer than the pre-industrial. Okay, and that warming is largely concentrated around the north, the Arctic. Okay, you might be able to just make out that most of these scenarios. So this is the lowest emission scenario. This is the highest emission scenario. So 2.6, 4.5, 6.0, 8.5. There's a little bit more warming over the land than the oceans. So that global average of 4 or 1.6 or something, if you're looking regionally, what you actually get will be different. Now, you can see at the moment, the short-term differences between these different emission scenarios, there's not much difference. They're all the same. You couldn't really tell the difference between making the choice to do some geoengineering and not do any geoengineering up here. They all look the same. Whereas if you go towards the end of the century, so the average climate in between 2080 and 2100, which is not so far away, if you decide to have children, this is them. There is a really drastic difference between kind of trying to sort out the problem and doing nothing and letting, let's burn some coal, yay, energy. You can see a huge difference in the average temperature, but also a much bigger contrast regionally. We've got much, much more warming in the Arctic than in the southern hemisphere, much bigger contrast between the temperature of the ocean and the temperature of the land. So this will have big regional impacts in terms of average temperature. It will also have big impacts in terms of the, changing the weather. If you change the contrast between different places on Earth, you'll change how the winds blow, how strong they blow, all this kind of stuff. And it's not just about temperature. It's also about precipitation. Precipitation is much more important, okay, to us than the temperature. Okay? If it gets too hot, okay, we could buy an air conditioner. Okay, that's got to run on some energy, right? But we could do that, or we could go inside, or live in a cave, or whatever. Right? If it gets too cold, we could buy a hat. Right? But if it stops raining, right, we got problems. Right? Because if it stops raining, then we're going to die of thirst. Okay? We could desalinize the ocean. We could get fresh water from the ocean. It's very energy intensive. It is possible, and it is becoming kind of more feasible. So I think Israel have got some really highly efficient desalination plants. But anyway, so let's look at what's going to happen. So we've got the four different emission scenarios. So this is basically us trying to sort out the problem, lowering the concentration of CO2 in the atmosphere. And you can see that actually there's not really much change. So where you've got this kind of this zigzag line across everything, that's basically the models projecting into the future, not really sure. Okay? Whereas where we've got these stipples, we've got dots. Okay? That means that the models are all agreeing that this region up here will probably get a little bit more wet. Okay? And actually, if you look at all of these, it looks like the whole globe on average will get more wetter, more rain. And that makes sense. If you heat the planet up, there'll be more evaporation, therefore more precipitation. The hydrological cycle will just get more active. And you can see if we go to let's go to this. Let's go to this one, which is I guess the least worst of the ones where we don't do geoengineering. So you can see here that the Mediterranean will get drier. So all of these countries that live around the Mediterranean, they're going to have lots of droughts, lots of fires, okay, lots of water shortages. Fewer people will be able to live there. Okay, we'll be able to grow less crops in those regions, all that kind of stuff. Whereas places like the Central Pacific, it'll rain more, but it doesn't really matter. That water will fall in the ocean, no big deal. But we might have more rainfall over kind of Bangladesh, the Ganges Plain here, might get a bit more flooding. And that gets much worse as we go to these higher emission scenarios. So the pattern of rainfall will change. So although the overall amount of rain will increase, it will get, I guess the extremes will get more extreme. So the drier places might get drier, the wetter places, more wetness. But those were all the averages of the average precipitation over a 20-year period. And that's, really, does anybody care about that? That doesn't really affect people in a big way. It might affect the long-term planning and things like that. But what really matters, what's really very destructive, are extreme events, both in terms of temperature and in terms of precipitation. Okay? It's not the kind of the average rainfall that washes your house away. It's the kind of the extreme precipitation event that causes a big flood. So this map in the middle, this is it's 2014, maybe. Heat wave, I think the next, no, 2015, close enough. There was a heat wave in Europe. It was very nice for us in the UK. It was kind of like lovely in great summer. But it killed a whole bunch of people in France because it was just so hot. Old people literally boiled to death in their own homes, which is very unpleasant, but it happened. So it's these extremes that matter. Okay? So what's going to happen to these extreme events? So this is some data from the Central England temperature time series. So this is one of the longest climate records where people were actually going out measuring the temperature with a thermometer back to, I think, like 1750. And you can see that what this is basically the maximum temperature in any one year. So some years, the maximum temperature was very cold. Okay, the maximum temperature was only 16 degrees Celsius. But usually the average temperature, usually the maximum temperature each year is around 22, 23 degrees. And then some years we have extreme warm summers where the maximum temperature goes up to 30-something in this particular part of central England. So it's these extreme warm events that we need to worry about. These are the ones that have caused damage to people. So I have to think about what happens to that part of that distribution of extreme events. So if we change the position of the mean of this distribution, if we just shift the whole thing, okay, to a little bit more warmer, so that knowing the average warmest day of the year, and that's going to get a bit warmer, that's not going to be a big deal. But it is a big deal because to the extremes, because what was only kind of this amount of likelihood, okay, getting above this temperature, okay, so if getting above this temperature is what caused there to be a problem, that used to be very unlikely, but now if we shift the whole distribution to warmer temperatures, then that becomes much more likely. Similarly, you don't have to just move the mean. If you just make the weather much more unpredictable, Okay, so you basically make the variance of this distribution wider. If that's this one, then that will also increase the likelihood of these extreme events happening. And obviously you could combine those two effects together, and that would make it kind of doubly worse. Okay. So this is a fancy, it's called a joy plot, after joy division. Those of you know, anyway. So the original distribution is what basically the temperature used to be at the beginning of the 20th century, on average, but with some range for each season. But then as the average has moved, okay, we've also the distributions have got wider. Okay, so this is quite an extreme example showing that actually the likelihood of us getting kind of a very much warmer event is now much, much higher. So we can look at how this will change in our climate models. So this takes a little bit of explaining as to what's going on here. So imagine that we have some kind of variability in, say, the temperature, and that's usually around some mean value, but it could be low or it could be high. Okay? So one measure of an extreme event is any temperature, okay, or any kind of average hot day that goes over this basically 90% line. Okay, so you've basically got a 10% chance of having an event of that amount of hotness or hotter. Okay, and then what you can do is to say if you fix that temperature for every point in your model, every point across the surface of your fake Earth in your little model, and you say, right, well, if I run my model over and over again and see how many times does that point go above that particular temperature. And if you don't change anything in your model, if you just keep it running under the conditions where you defined this variability, then it should stay at every 1 in 10 years, you should get something above that threshold temperature. So you should have a 10% likelihood of exceeding that value. And that's what should happen if nothing changed. So if nothing changed from 1960 across, this line should follow the 10% exceedance rate, so across this plot. But that's not what happens because we've changed the climate, we've warmed the average, so we're making it now much more likely, so I guess we're up here, so we're now 20% chance of exceeding this value here. So we've basically, in the model, by changing the temperature, we've moved the distribution over to the right to higher temperatures, and now we're more likely to have kind of an extreme warm event. Okay. There's another way that you can think about these extreme events, and that's in terms of the return period. So you could look in your climate model, if you run your climate model under conditions with no extra greenhouse gases, and you could say, well, what's the amount of rain that you get, kind of like an event, a big storm that happens maybe on average once every 20 years. Okay, so that's like a 20-year event. It doesn't actually happen like, oh, we've had 19 years and then the 20th year there's a big flood. But on average, because you can run your climate model for thousands of years under the same kind of climate conditions to get an average of how often you get a kind of a rainy event that is kind of on average 1 in 20 years. And then you can see, as you model through time by changing the climate, how does that frequency of that kind of event change? Okay, and that's what's plotted on the second figure and in this map along the bottom. So as you go through time, what used to be a maybe 1 in 20-year event becomes maybe a 1 in 10-year event or a 1 in 5-year event. So that change in the relative change, that's the relative change in the return period from 20 to 10 or so on. So just looking at this map here, so this is looking at the return period of a 20-year wettest day. So they look across all of the data from model runs which are run under non-greenhouse gas forcing conditions and just say, right, what are the wettest days? Okay? And they pick an amount of wettest day that basically would then occur once a year on average once every 20 years. And then they run it into the future using greenhouse gas forcings, and you see that these regions, so basically all of the blue regions, okay, what was once a 1 in 20 year effectively bad wet day now becomes maybe a 1 in 4 year, or in some places 1 in 2 years. So every other year you've changed it by a huge amount. Okay? Whereas some regions, you see here, are now getting more than 20 years. So what was a 1 in 20 year event, that region is now so dry that might be now 1 in 30 years, 1 in 40 years. So we can see that the kinds of changes we're going to expect in the future are not just average temperature rise, nor not just average precipitation increases. We're going to get spatial variability in terms of those average temperatures and average precipitations, but also changes in things like heavy precipitation events, extreme heat waves. Okay? They are going to become much, much more likely. Another thing that's going to be changing is sea level, because if we make the planet warmer, that energy will go into the ocean and sea level will rise. So we can look at what's happened over the past. So over the maybe tens of thousands of years, we used to have big ice sheets that locked up water. That means sea level was lower. But for the past maybe 6,000 years, sea level appears to be quite constant. Okay? So it hasn't been changing for thousands of years. But if we look at recent records, so these are various records either from satellite altimetry or measuring from tide gauges, we can see that the ocean level has been rising quite uniformly. And that's because we've been heating the planet. And we've been heating up the water, and the water then expands, and therefore sea level goes up. So we can try and get to use proxies to see this difference between the long-term trend of sea level before we altered the climate, and these are estimates based on, I guess, proxies for past sea level. So these are basically the elevation of fossil salt marshes, and we can see that sea level was fairly constant, maybe went up a little bit over 500 years, and then was kind of constant again, until we get to kind of like the beginning of the 20th century, and we see this big increase in the rate of sea level rise in this particular place in the US. So the rate of sea level rise we're seeing at the moment really is anomalous. And we can attribute that to where it's coming from. Okay, so we can basically put these things into from our climate model. We know how much, how much energy is going into the kind of the atmosphere, and how much the ocean is warming, and we can then predict how much sea level will rise. And that's what's done here. We can see just projecting into the future with different emission scenarios. We have, by the end of the century, an average of maybe up to 75 centimeters of sea level rise. Now the thing is, if we look about what goes into that prediction, okay, which is kind of over here, you can see that it's made up of things like, well, first of all, thermal expansion. So that's just us heating up water and it expanding and getting a bit bigger. But the terms, the other terms, which are smaller components, so this is the thermal expansion, and these are all the other ones here. Things like melting glaciers, that's the blue line. And then melting ice sheets so the big ice sheets, Greenland, Antarctica, they're not really, in this scenario, we're not really including them. They're saying they're not going to melt. Okay? Which is ridiculous, because they absolutely are going to melt, and they're really big. Okay? So by just changing, so basically these estimates of future sea level rise are almost certainly an underestimate of what will actually happen, because our ice sheets, okay, are melting, okay, and that is not currently in those estimates. And this will have a big impact around the globe, but also to us here in the UK. So it's more of a problem for England than Scotland, because Scotland has quite steep edges. So when sea level rises, the water doesn't come in much. So it's a big problem for London. Okay, so the Thames barrier will probably be overwhelmed some part later on in this century. So we'll need to build another one at a cost of many billions of pounds. So 1 to 2 meters of sea level rise would be, pretty disastrous for London. I can't remember the name of the place. It's somewhere on the south coast. want to say Dungeness, but it might not be Dungeness. But we have, in our infinite wisdom, built a nuclear power station here, right, on a sandbank. It's so stupid. Anyway, the fens, so this is land that really should be underwater anyway, around Cambridge. And actually, in the news this morning, rising sea levels around the English coast will cause, we're going to lose a lot of homes, and it's going to cost a lot of money to try and fix. So much money that we're not going to bother doing it. But it's not just about us. There are other people in the world as well, and they do matter. So the red area here is stuff, if we had even 6 meters of sea level rise. So this is towards the very extreme end members. This won't happen this century at all. But in the centuries to come, all these places will be underwater. And the red areas are also where lots of people live. So this is the, the river that goes through Shanghai. It's, that delta, okay? So these places are going to be very, very underwatery. Can't remember why I put that in. So the problem is CO2, okay? CO2 is bad, and we've been putting it into the atmosphere. So this is a record from an ice core, and you can see that over the last 400,000 years, we've had these glacial, interglacial cycles of CO2 varying by maybe 100 and something parts per million. And this is due to these feedbacks in the climate system between temperature and the solubility of CO2 in the ocean and things like that. We are currently, I didn't change this at all, but we're currently just above 400 parts per million. If you go to, do you know Summer Hall? Yeah, there's that big tower block next to it, and on the top of that, it tells you what the CO2 concentration is at the road level. Yeah? So I think this morning it was 430 something. But that's because we're in a city and there's lots of cars belching out lots of carbon dioxide. But the annual average global is around 400. So we're already kind of double, really, the LGM value. We've basically changed the amount of CO2 in the atmosphere by an amount that is similar to that has changed across a glacial interglacial cycle, which is a huge environmental change. You saw the video of this playing before, and where we could see the actual sources of that CO2 coming out of our industrial centres. This will be shown in the we'll talk about this kind of thing in the last part of the course, but you can see there are interesting features in the CO2 climbing up through time. So we can see this is going forward in time here. This is the northern hemisphere, the southern hemisphere. There are big swings annually, okay, mostly more pronounced in the northern hemisphere. So there are fluxes in and out of the atmosphere on very short timescales, which are entirely natural. But the overall trend is due to us. So this, hopefully you will have seen a plot like this. If you've done the practical, you will see another one. Yeah, it's going up and up and up, up and up and up and up. And that's affecting this emissivity, E, which is warming the planet. But are we doing anything about it? So this is some news articles that came out, I guess, before, last year and the year before. So the graph here is showing the amount of carbon we put in the atmosphere every year. So this is basically just an accounting exercise of working out how much fuel we've burnt and it's gone into the atmosphere. And you can see for the last 3 years there, 2014, 15, and 16, it looks like we're leveling off. We're not putting much more into the atmosphere every year. Okay? So that our rate of burning fossil fuels has flattened off. Turns out that that's stopped happening. So that was 2014, 15, and 16. Those are the amounts each year are the black bars. And then what we've got here is for each of these little blocks is in between 2015, 2016, say the US has reduced by 0.1 gigatons, China's done no change, the rest of European Union no change, India have increased by 0.1 gigatons, and then the rest of the world by 0.15. So you can see what happened in between 2016 and 2017. China and the rest of the world went nuts for burning fossil fuels again. And that's because they make our stuff, right? See, all of the things, the MacBooks that you've got out, turn them over, made in China, yeah, that's you. It's not just China. We can change the amount of fossil fuels we burn into the atmosphere. So this is, again, the emissions, gigatons of carbon per year. And you can see the different parts of the world economy. So China's in red. I can't remember which Europe is. But through time, these things have been increasing. But there are things we can do. So, for example, if we have a global war, okay, we can reduce our CO2 emissions. I mean, that's pretty good. If we can completely collapse the economy, yeah, global financial crisis, we can change the amount we, by a bit, right, to start, right? But the problem is that those rates are totally irrelevant, because it's not the rate in which we add carbon to the atmosphere that matters. It's the amount in the atmosphere that matters. So what matters is the cumulative emissions, the total amount that we've added into the atmosphere. And you can see that those little changes in the rate have no effect whatsoever on the amount. Okay, that's still going up. Okay, so we want to make our emissions to 0 and below, so actively taking it out of the atmosphere, not just reducing it a bit. And the reason, I mean, this is another kind of way of demonstrating that. So this is a plot showing the total amount of carbon in the atmosphere across the bottom. This is total amount of carbon, total amount of CO2. That's why the numbers are different, because that's the difference in the mass between CO2 and carbon. And then the amount of warming that you get. And you can see the different coloured lines on here are these different emission scenarios. And it doesn't matter, which of these you take, because any given amount of carbon will cause an amount of warming. It doesn't matter how fast you put it into the atmosphere. Once it's in there, you pretty much know what the temperature is going to be. Okay? So you can see that the red gets up here faster than the blue, but they basically follow the same line. So this is our choice. This is where we are at the moment. So we need to get to emissions of 0 and actually below. And we are currently here, and we've just gone up a little bit, and we need to come down. And the longer we delay reducing our emissions, the more painful it will be, the steeper the drop-off will have to be. Until we get to some point where, this line becomes vertical, which will probably be about 2040, maybe just before. And when we get to that point, there is no way at all where we will be able to limit the global warming to less than 2 degrees Celsius, which will be pretty catastrophic. So, that was fun. To finish on a high note. So I guess this really is some of the problems that you're going to have to deal with for your scientific careers. These are lots of problems that need fixing, so please fix them. The summary of the lecture. So from basically our climate models comparing climate runs with and without greenhouse gas forcings, that basically proves that we need to have CO2 to explain the warming. So that says that CO2 is the cause of it. When we're modelling these emissions scenarios into the future, it's really important for us to get an understanding of how our economy works. Okay, how our population is going to grow, how our efficiency, or basically carbon efficiency per dollar, is going to go. But into the future, when we're modelling these impacts, they rely really heavily on not just the average. Okay, no one cares about the average. It's the extreme events that are damaging to society and to people and to the economy and to insurable value and those kind of things. I guess sea level rise I have in here. Sea level rise is probably the one thing you can't really get away from. Okay, if it's hotter, you can put a sun hat on. If you get more hurricanes, you build a stronger house. But if sea level rises, you can't live underwater. Right? You have to move your city uphill. Okay, which is very, very expensive, especially if you live in a coastal plain where moving your city means moving it a very long way. And then the last point is probably the most important. It's the total amount of carbon in the atmosphere that matters. It does not matter how fast we add it. That just is like us delaying the problem. Right? We need to remove carbon dioxide from the atmosphere, probably, if we're going to survive beyond the next century. So fun times with carbon dioxide. Yeah, so that's us done now. There is 90% sure there will be a tutorial on Monday. You will have been signed up on Learn to a tutorial group. Now, that might be a tutorial about chemistry, kind of preparing you for the lectures, but Brian is a bit ill, so it might not. So if Brian is not well, then we will do something else. So the tutorial is, the chemistry part of the tutorial would have been, for those of you who don't have any chemistry, higher or A-level or whatever, to prepare you for the chemistry part of the lectures. But do come along if you have that chemistry background anyway, in case Brian doesn't turn up and it's me doing something else, which will be probably going over some of the questions that I've been posting on the forum here, but also showing you some referencing software, which you should know about. Anyway, yeah, so check which group you're in. I don't really care if you turn up to the wrong session, but, you know, you've got to have groups, right? Yeah, we're done. So if you've not signed in, can you sign in, please? The sign-in thing is there. That would be super awesome. Yeah, but we'll probably have to have the question outside.
Yeah, that's fine.
Yeah. Right, log off. We're going to have to just outside because